Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is chapter 2.4, which is on the complex numbers. Alright, so before we talk about the complex numbers, let's talk about the imaginary unit I. And here, I is defined to be the square root of -1. Alright, so from that, we can deduce a few things. We can say that I squared is, well, that would be the square root of -1 squared. Square roots and squares cancel each other out, so -1. I to the third would then be I squared times I. I squared is just -1, so in here, what we're looking at is just -1 times I, which ends up being just -I. I to the fourth would then be, well, I squared times I squared, which would then be -1 times -1, which is just +1. Right? And we didn't have to look at it that way. We could have looked at it as I cubed times I, and then we know what I cubed is. I cubed is -I, so we have -I times I, which would then be -I squared. But I squared is -1, so we have the negative of -1, which ends up being +1. So either way, we get the same value, 1, right? Now that we know that I to the fourth is 1, that leads to a very cool conclusion here. So let's see what happens after I to the fourth. So we're going to say, well, we have I to the first was just I. I squared was -1. I cubed was -I. And I to the fourth was 1. Now, I to the fifth. I to the fifth is going to be I to the fourth times I. And I to the fourth was just 1, so we have 1 times I, which is just I. I to the sixth is I to the fourth times I squared. I to the fourth was just 1, so we have 1 times I squared, which is just I squared. Right? But I squared was -1. I to the seventh, we have I to the fourth times I cubed. I to the fourth was 1. I to the cubed was -I, so we have 1 times -I is just -I. And I to the eighth would be I to the fourth times I to the fourth, which would then be 1 times 1, which ends up being just 1. And look at that. I, -1, -I, 1. I, -1, -I, 1. So I can right away tell you what these next values would be. I to the ninth, I to the 10th, I to the 11th, and I to the 12th. This is going to be I, -1, -I, 1. All right, and it's a pattern that repeats after every 4. That fact that it's a pattern that repeats after every 4 repetitions of this, it allows us to come up with a cool way to figure things out. So let's see what I mean. So I'm going to say simplify the following. Example A. Let's say that I had something like I to the 337. All right, and we want to figure out what that is. Well, what was the pattern up here? It was after every 4. So what we're going to do here is we're going to take our number here, 337, and we're going to divide that by 4. All right, and we're going to say, well, how many times does 4 go into 337? Well, how many times does 4 go into 33? 8 times. Subtract. How many times does 4 go into 17? 4 times. Subtract. What we care about here is our remainder. All right, because this remainder, it's actually going to tell us that what we have here is equal to, well, let me do it this way. This remainder is what we're going to work with. And we're going to say that I to the 337th is equal to I to the 1, because that was our remainder. So this is just equal to I. And that was supposed to be an equal sign. There we go. Way better. Good job. Now, let's do another one. Notice again, I divided our exponent by 4, and I took a remainder of 1. And this 1 corresponds to all these exponents, all right? Anytime we divide by 4, there's only 4 possible remainders. So that's what these correspond to. Next one. So let's say that I have I to the, no, let's not do 3, 663, all right? I to the 663. And in here, well, what are we going to do? We're going to take 663, divide that by 4, right? And we say, well, 4 into 6 is 1. 1 times 4 is 4. Subtract. Bring down the 6. 4 into 26, that's 6. 6 times 4 is 24. Subtract. Bring down the 3. 4 into 23 is 5. 4 times 5 is 20. Subtract. Remainder 3. And this is what we care about, because now what we have here, this tells us that I to the 663 is equal to just I to the third. And I to the third, we knew that to be just negative I, so that is our answer, negative I. All right, and again, that's from here. Now, let's do another one. Let's say I had something like I to the 748. All right. And here we start the same way. We say 4 into 748, or 748 divided by 4. And say 4 into 7, that's 1. 1 times 4 is 4. Subtract 3. Bring down the 4. 4 into 34, that's 8. 8 times 4 is 32. Subtract. We end up with a 2. That's supposed to be a 2. There we go. Bring down the 8. 4 into 28, that's 7. 7 times 4 is 28. Subtract. It's 0. All right. So now we say, well, we look at our remainders. Which one of those is I to the 0? Well, here's the thing. This part right here is equivalent to I to the 0, right? Because any constant to the 0th power is just 1. So there's an invisible thing that says here, I to the 0 is just 1. Or you can think of it as I to the 0 is just equal to I to the 4th, and therefore it fits all of these, all right? All the multiples of 4 there. So we have then that this implies that we have I to the 0, which is just 1, all right? One last one, and then we move on. So D. Let's say that we had something like I to the 530. Let's do 534. There we go. Well, we're going to start the same exact way. Take 4 and divide it into 534. And we say 4 into 5 is 1 time. Subtract, remainder 1. So 4 into 13 now is 3. 3 times 4 is 12. Subtract, remainder 1. 4 into 14 is 3. 3 times 4 is 12. Subtract, remainder 2. So now we have here, that's what we're going to work with. We're going to say that this implies that I to the 534th is equal to just I squared, which is equal to, not 1, negative 1. There we go. All right. So that is the workings of the imaginary unit I. Now, let's talk about the complex numbers. So definition of the complex numbers. All right. So this is what it says. It says for elements A and B that are elements of the real numbers, so for A and B being elements of the real numbers, A plus BI is called a complex number in standard form. Where I is the imaginary unit. All right. This has two components. It has a real component and an imaginary component. So in here, A is called the real component, right? And B is called the imaginary component. All right. Now, in here, let's talk about how these numbers exist. All right. You may recall at one point seeing something like this, that we have the natural numbers, right? Which are like the counted numbers, like 1, 2, 3, 4, so on and so forth, right? And then after the counting numbers, there were the whole numbers, where the whole numbers were 0, 1, 2, 3, 4, so on and so forth. After the whole numbers, we had the integers, right? Which were the positive and negative versions of all the whole numbers as well. After those, we have the rationals, which were things like fractions, right? And in here, after rationals, outside of rationals by itself, were irrationals. And then all of these together, with the powers combined, were the real numbers. And by the way, perhaps I should mention here, the irrationals were things like pi, e, the square root of 2, so on and so forth. And then all of those combined were the reals. Well, the complex numbers exist beyond the reals. So it is true to say that real numbers are complex numbers, but complex numbers are not necessarily real numbers. Here in the complex numbers, that's where we have a plus bi. All right. Now, let's talk a little bit. So that's a little more number theory for you. Let's talk a little bit about the equality. So a couple of definitions, really. The equality of complex numbers. It says if we have two complex numbers and you set them equal to each other, well, this implies that, so like for these two complex numbers to be true, this is only true if and only if, maybe I'll write it this way, if and only if A is equal to C and B is equal to D. So it's only true if the the real part is equal, if the real parts are equal to each other, and if the imaginary parts are equal to each other. All right, our components. All right, so now the sum and difference rules. Sum and difference of complex numbers. So if I have a plus bi and I'm adding some other complex number, well, what we do is essentially we combine like terms, and we say, well, the like terms are the real components are like terms and the imaginary components are like terms. So we say, well, this is going to be a plus c plus c plus d I. All right, so that's the sum. The subtraction, essentially the same thing. That's not what I meant. Minus. So I'm subtracting two complex numbers. Well, you subtract them real components, and oh, look at this. I messed that up. This one B. There we go. Imaginary components, B and D. And over here, the imaginary components, B plus D, I. There we go. And that plus, we were subtracting. See what happens when you mess up? All right, done. So essentially, we subtract the real components and subtract the imaginary components. So let's go ahead and do some examples. So that we are at That last one was E, so F. So here I'm just going to say evaluate the expression, or just evaluate. So F. Let's say I had something like 7 plus 3i plus 5 minus 4i. Alright? Well, what did we say we did? We have to add the real components, so we have 7 plus 5, and add the imaginary components, 3 minus 4, right? 3 plus negative 4. And what we end up with here is just simply 7 plus 5 is 12, and 3 minus 4 is negative 1, so we have just negative I. Done. Next one. Let's say that we had something like 1/3, and that was supposed to be a 3. 1/3 minus 3/5 I plus 2/5, negative 2/5, excuse me, minus, actually let's do it this way, minus 2/5 plus 2/3 I. Alright, so here now we have fractions. So the very first thing that you should do in problems like these where you have fractions is get rid of the fractions. And how are we going to get rid of the fraction? Well, essentially what we need to do is have a common denominator. So we need to have a common denominator. I'm also going to distribute this negative. You know what? Let's distribute the negative. So in here, if I distribute the negative, I have 1/3 minus 2/5 plus negative 3/5 minus 2/3, right? And then here I'm taking this definition, right? When we subtract them, it's A minus C plus B minus D. A minus C plus B, B is negative 3/5, minus D, and these, so minus a positive 2/3, all right? And here, have a common denominator. I'm going to say the common denominator is 15, so this is going to be something over 15 plus something over 15 as well on this side, I. And what do we get for the numerators? Well, to go from 3 to 15, multiply by 5. To go from 5 to 15, multiply by 3. So 2 times 3 is 6. To go from 5 to 15, multiply by 3. To go from 3 to 15, multiply by 5. And what we get now is 5 minus 6 is negative 1, so negative 1/15. And then negative 9 minus 10 is negative 19 over 15i. You could think of this as a plus negative 19 over 15, but then plus a negative is just negative. All right, so there we go. And there we have it. Notice that I left these separately, all right, because you always want to write your solution, your final answer with a complex number. You always want the simplification to be in standard form, so a plus bi. And here our a is negative 1/15, and our b is negative 19/15, all right? But you want to write it as a plus bi. All right, let's do another one. So let's say that I had something like 1/14 plus 2/7 I minus 3/2 plus, not 6, 9/14 I. All right, so in here we're going to come up with a common denominator. All right, but well, first let's actually split this up into the real parts. So 1/14 minus 3/2 plus, now the imaginary components, 2/7 plus 9/14 I. And then we say we'll come up with common denominators. In both of these cases, the common denominators are 14. And what do the numerators become? Well, to go from 14 to 14, it's already there, so we leave the top as is. To go from 2 to 14, multiply by 7, so 3 times 7 is 21. To go from 7 to 14, multiply by 2, so 2 times 2 is 4. To go from 14 to 14, it's already there, so leave the top alone. And what we get here as a final answer now is just negative 20 over 14 plus 13 over 14i. But you should always reduce. Here, these are both even numbers, so they're definitely divisible by 2. So we end up with negative 10 over 7 plus 13 over 14i. And that will be our final answer. All right. And again, notice that I have this as a plus bi. All right. You always want to put your final answer of complex numbers that way. All right. So now, that was addition and subtraction. All right. So let's talk about multiplication. All right. So multiplication of complex numbers. And the answer is simple. How do we multiply them? Well, treat them as binomials. What do I mean by that? Well, if I have a plus bi times c plus di, if I'm treating this as binomials, well, what I mean here is FOIL them. So what we have, a times c plus a times di plus b times, or bi times c, so bci, plus bi plus di, or excuse me, bi times di, so bdi squared. All right, and then we know that I squared is just negative 1, so we can have here AC minus BD plus AD plus BC. I was supposed to say BC. BC, there we go. I. All right, that's what you end up with. Now, do I expect you to memorize it from here to here straight through? No, I expect you to know how to FOIL this. All right, know how to FOIL this. So let's multiply. So we were at I. So let's say that I had something like 2 minus 4i times 3 plus 3i. And what we're going to say here is where we FOIL it. So 2 times 3, I'll do it on the next line. 2 times 3 is 6. 2 times 3i is 6i. And that was an I. 6i. Negative 4i times 3 is negative 12i. Negative 4i times 3i is negative 12i squared. Right? And then at that point, we know that I squared is just negative 1. So in here, I squared is negative 1. So we can say that this is actually 6 minus 12 times negative 1. Well, let's do it this way. And here, 6i minus 12i, that's clearly just negative 6i. But over here, we have negative 12 times negative 1. Both of those combined are just a plus or a positive 12. So we have 6 plus 12, which is 18. And then we have 18 minus 6i. And again, notice it's in the form of a plus bi. All right. Let's kick it up a notch. Okay. Let's say that I had something like negative 2/3 plus 1/6 I times 1/4 minus not 1/4. Yeah, why not 1/4? 1/4 minus 3/5 I. All right. So here we go. Well, we're going to FOIL it. So we have here negative 2/3 times 1/4. That's negative 2/12. Well, you could also think of it as the 2 and the 4 reducing. So you know what? Let's actually write it down. We're going to say we have negative 2/3 times 1/4. And then plus negative 2/3 times negative 3/5 I. Right, so the I. So that's the first, the outer. The inner is going to be 1/6 times 1/4 I. And then the last one, plus, well, positive times a negative. we're going to end up with a negative there, but we can just think of it as 1/6 times negative 3/5 I. So let's see what we get. We're going to reduce. 2 becomes a 1. This 4 becomes a 2. This 3 becomes a 1. This 3 becomes a 1. Nothing to reduce there. This 3 becomes a 1. This 6 becomes a 2. So what we really have here is negative 1/3. A negative times a negative is a positive, and then we have 2/5, so plus a positive 2/5 I, plus 1/4 times 1/6 is just 1/24, and we have that as I. And lastly over here, positive times a negative is going to be negative, and then 2 times 5 is 10, so negative 1/10 I. And that's supposed to be I squared. Look at that. I times I should be I squared. And then I squared, let's, I squared, oh, we want that there. But I squared is just negative 1, right? So in here, this is just negative 1. So we have here negative 1 times all of this. Well, negative times a negative now is going to be a positive. There we go. So we fixed that. Good. Let's continue. So now, in here, we need to make sure we have common denominators. So, well, I'm going to just put the negative 1/3 plus 1/10 there, plus 2/5 plus 1/24 I. In other words, I'm combining the real components and the imaginary components. Coming up with a common denominator, 30, to go from 2 to 30, multiply by 10. To go from 10 to 30, multiply by 3, plus common denominator here. Well, 5 doesn't go into 24 at all, so this is going to be the product of the two. So 5 times 24, so 5 times 20 is 100. 5 times 4 is 20, so it's 120. To go from 5 to 120, we multiply by 24. 2 times 24 is 48. To go from 24 to 120, we multiply by 5, so 1 times 5 is 5. And in here, as our final answer, now we would say is negative 10 plus 3 is negative 7. So we have negative 7/10 plus 48 plus 5. 48 plus 5 is 53. So we have 53 over 120 I. And that doesn't reduce at all. So next one, K. Let's say that we have something like 4 plus 2I squared. All right. Well, in here, we can do two things. We can either write this as 4 plus 2I times 4 plus 2I and then expand it, right, and FOIL it. Or we can realize that this is in the same exact form as a plus b quantity squared, right? Or I should say a plus bi quantity squared. And what would that be? That would be a squared plus 2abi plus bi squared. But bi squared is just, well, b squared times I squared. And I squared is just negative 1. So we can write this as a squared plus 2abi minus b squared. All right. So essentially, just remember how to expand this, right? A plus b squared. So we can say then, maybe I'll write it over here. 4 plus 2I squared is going to be 16, right? The first one squared, plus twice the product of these two. 4 times 2 is 8 times 2, 16. So 16I, right? 4 times 2 times 2. And the last one squared, well, it's going to be minus 4 because of this, right? Again, in here, you can think of this as it's saying 2I squared, which is 2 squared I squared. But 2 squared is just 4, and 1 squared is just I squared is just negative 1. But anyway, so there we go. 16 minus 4 now is 12, so we have 12 plus 16i as our final answer there, right? Now, let's talk a little bit about something called complex conjugates, right? And if you remember conjugates, well, before the conjugate of, so the conjugate of A plus B is A minus B. So with complex conjugates, it's going to be basically that. But it's going to say the conjugate of A plus BI is A minus BI. And similarly, the conjugate of A minus BI is A plus BI. All right. So let's talk about the product of conjugates. The product of complex conjugates. So what am I saying here? So let's take A plus BI times A minus BI. And what does that give us? Well, let's remember first what the product of conjugates is. So if I have A plus B times A minus B, this should remind you of the difference of squares. All right, so let's apply that here. Instead of B, I've got BI. So what I'm going to get here is A squared minus BI squared. And what is BI squared? So let's say that's going to be minus B squared times I squared. But then I squared is -1. So what we have here is A squared. Well, -1 times negative B squared is positive B squared. So A squared plus B squared. So look at that. What we found here is that the sum of squares can be factored into complex conjugates. All right. Or that the product of complex conjugates gives you the sum of squares. So let's see what we can do here. So what letter am I at? Okay, so L. Let's say that we had something like 3 minus 2i times 3 plus 2i. Well, this is just the product of complex conjugates, so it's the sum of squares. So 3 squared is 9, plus 2 squared is 4, so 9 plus 4 is 13. And you can try it out if you want to do this a long way, right? You can say this is 3 times 3 is 9, 3 times 2 is 6i, negative 2i times 3 is negative 6i, negative 6i, and then negative 2i times 2i is negative 4i squared. But in here, these two cancel each other out. Then I squared is -1, so we have 9. Negative 4 times -1 is positive 4. So we still get 13. But look how much longer that was. So if you can recognize that you've got the product of conjugates, go ahead and do just the sum of squares. Right? So if I have something like 7 minus 6i times 7 plus 6i, I know right away that this is just 49 plus 36. And then we say, well, at that point, 49 plus 36 is, well, 9 plus 6 is 15, carry the 1, 4 and 3 and 1 is 8, so 85. All right. So the product of complex conjugates is relatively simple. So if I have -2 plus 3i times, well, let's not do 3, let's do 5. -2 plus 5i times -2 minus 5i. Well, again, right away I know that this is just 4 plus 25, because it's just -2 squared, 4, and then 5i squared, well, -5i squared becomes that. And that gives us just simply 29. Cool. So that was multiplying by conjugates. Now, that's a lot of multiplication. Let's talk about division. How do we divide complex numbers? So now, division. Division of complex numbers. Well, it's simple. We treat them as fractions. what do I mean? So if I have a plus bi divided by c plus di, what I'm going to say is I'm going to treat this as a plus bi over c plus di. And then I'm going to do all sorts of tricks to rewrite that. So let's see. Divide. Let's do 3 plus 7i by, or let's do it this way, divided by 2 minus 5i. Alright, so in here, I said I'm going to treat them as if it was a fraction instead of division. So 2 minus 5i. Alright, but the thing is, we need to have our answer in standard form, right? We know that with complex numbers, we're going to put them in standard form. So what can we do here? Well, we can always do two things to any math problem. We can always multiply by 1 or add 0. In this case, we're going to multiply by 1. But the 1 is going to be chosen very carefully. We're going to multiply by the conjugate of the denominator. So I have 2 plus 5i and 2 plus 5i. Alright, so in here, notice this fraction is just equal to 1. So now, what does that give us? Well, on the bottom, we've got the product of complex conjugates. We already know that that is the sum of squares. Done. On the top, well, we got to FOIL that out. 3 times 2 is 6. 3 times 5i is 15i. 7i times 2. Oh, hold on. Oh, no, that's fine. 7i times 2 is 14i. And then 7i times 5i is 35i squared. But we know that the I squared is going to turn this into just simply a negative 35. So what we have now is 6 minus 35, that's negative 29, plus 15 plus 14 is 29, not 19. 29, so we have 29i. All of this over 29. So what we get here really is, we have to write it as two fractions, so negative 29 over 29. Plus 29 over 29i, which is simply negative 1 plus I, right? 29 over 29 is just 1. All right, so next one. So example P. So let's say we have 6 minus 2i over negative 3 plus 7i, and then we're going to have that plus 5 minus 3i over, let's say, 7 minus 3i. All right. So let's see what we're going to do here. Well, what we're going to do here is essentially what we did in example O, but we're going to do it twice. So let's see what we mean. So what we're going to say here is this first one, 6 minus 2i over negative 3 plus 7i. That one, I'm going to multiply it by its conjugate. So that's going to be by negative 3 minus 7i over negative 3 minus 7i. And again, notice that here what we're doing is multiplying by 1, because multiplying by 1 does not change anything. And then we have this plus 5 minus 3i over 7 minus 3i. And we're going to multiply this by the conjugate of the denominator over itself, because again, that's just equal to 1, and multiplying by 1 changes nothing. So at this point, well, look at the denominators, and here I have the product of conjugates. The product of conjugates is the sum of squares, so 9 plus 49. Product of conjugates is the sum of squares, so I have 49 plus 9. In the numerators, I need to actually FOIL it out. So 6 times negative 3 is negative 18. 6 times negative 7 is negative 42i. Negative 2i times negative 3i is a positive 6i. Negative 2i times a negative 7i becomes a positive 14i squared. The other one, 5 times 7 is 35. 5 times 3i is 15i. Negative 3i times 7 is negative 21i, and negative 3i times 3i is a negative 9i squared. Now, in here, This piece right here is going to become just negative 14. How come? Because I squared is negative 1. 14 times negative 1 is negative 14. This piece right here is going to become a positive 9. How come? Because I squared is negative 1, and negative 9 times negative 1 is positive 9. So, what can we say now? Well, what we have now here is, well, 9 plus 49 and 49 plus 9 are the same thing. So we can put all of this over the same denominator, that denominator being 58, right? 49 plus 9. And on the numerator, well, let's see. We've got negative 18 minus 14, that's negative 32. And then negative 42i plus 6i, that's going to be negative 36i. And we have that plus 35 plus 9 is 44. And 15i minus 21i is negative 6i. The next thing is, well, combine like terms. Negative 32 plus 44 is going to be 12. Negative 36 plus negative 6 is going to be negative 42i. And then we have this over 58. But we know that we need to have it in standard form, so we need to split this up into 12 over 58 minus 42 over 58. But we also know that we need to reduce as much as possible. 12 and 58, well, they're both divisible by 2. 12 divided by 2 is 6. 58 divided by 2 is 39. And then between 6 and 39, let's actually do a different color for that. Between 6 and 39, 6 divided by 3 is 2. 39 divided by 3 is 13. So there we go. It becomes 2 over 13. And then for 42 and 58, well, they're both divisible by 2, right? So 42 divided by 2 is 21. 58 divided by 2 is 39. And then once again, they're both divisible by 3. 21 divided by 3 is 7. 39 divided by 3 is 13. So my answer here now is minus 7 over 13i. All right. And again, standard form, a plus bi. All right, cool. So that's division, technically. And then, well, in example O, it was division, but now we combine division with addition, right? So that's essentially just a lot of arithmetic for complex numbers. Now, let's talk about something called the principal square root of a complex number, of a negative number, excuse me. Let's spell it correctly. Principal square root of a negative number. All right. So it's pretty simple. If I've got the square root of negative a, this is going to be the square root of negative 1 times a, which is just the square root of negative 1 times the square root of a. But the square root of negative 1 is just I, so what we have here is I times the square root of a. You can also think of this as the square root of a I. And you can also rewrite it as, if you really wanted to, as the square root of a I with parentheses around it. I tend to stick to one of these two, depending on my mood at the moment. But yeah, so what do we mean there? So let's say, so if I had something like, well, let's do an example. What letter am I at? P, so Q. Let's say that I had something like the square root of negative 36. All right, well, this is just the square root of negative 1 times the square root of 36, which will be then I times 6, so just 6i. All right, that wasn't too bad. R, the square root of negative 49, 7i. Right, because the square root of 49 is 7, and the square root of the negative makes it an I. S. Let's say that I had a product of something like this. So let's say I had the square root of negative 3 times the square root of negative 12. Now, in here, first I'm going to do it the wrong way. All right, this is what I don't want you to do. But it's very simple to make this mistake. So this is the wrong thing. I've got the square root of negative 3 times the square root of negative 12 is equal to the square root of negative 3 times negative 12. So that's the square root of, well, negative 3 times negative 12. Negative times a negative is a positive. 3 times 12 is 36. So therefore it's 6. That is wrong. All right? That is wrong. And it's a very simple thing to miss as to where the mistake is. In fact, the very mistake happened from here to here. All right? That's where the mistake happened. Let me show you what the correct thing is. And this is what you need to be doing. The square root of negative 3 times the square root of negative 12. Well, by definition, this is just the square root of 3i times the square root of 12i. Right? At that point, now that becomes the square root of 3 times the square root of 12 times I times I. The square root of 3 times the square root of 12, that's the square root of 36. I times I is I squared. The square root of 36 is 6. The I squared is negative 1. So we get negative 6. All right. So again, the mistake happened from the very first step on this side because you're completely ignoring the definition of the principal square root. You need to have it as I. If I have a negative in there, it becomes I times the square root of A, or the square root of AI. All right. When you do it this way, you completely miss that. So make sure you do this. All right. Now, so that was S. C. Let's say that I had something like the square root of negative 3 times the square root of negative 75. All right. Well, you can think of this as the square root of 3i times the square root of 75i. All right. And that's going to give me, well, 75. Let's rewrite that. Square root of 75 would be just, well, that's 3/4, right? 75 cents is 3/4. So you can think of square root of 3 times the square root of 25. And then I times I is I squared. So what we really have here, square root of 3 times the square root of 3 is just 3. Square root of 25 is just 5. I squared is just negative 1. So we end up with negative 15. All right. Next one. So let's say that I was adding them. The square root of negative 48 minus the square root of negative 12. But what do we do here? Well, simply stated, we simplify. The square root of negative 48 is radical 48i minus the square root of negative 12 is radical 12i. And then what do we do? Well, we try to see if we can reduce the square root of 48. Well, 48 is 16 times 3, the square root of, so I'm going to write this as the square root of 16 times the square root of 3i minus, and the square root of 12 is the square root of 4 times the square root of 3i, and then the square root of 16 is 4, so 4 radical 3i, minus the square root of 4 is 2, so 2 radical 3i, and then they're both like terms, they both have radical 3i's, so 4 minus 2 is 2. So 2 radical 3i would be my final answer there. All right. Now, V. Let's say that I had something like negative 1 plus the square root of negative 3 squared. Well, again, the very first thing you need to do here is rewrite this. Don't leave it in that form. Rewrite it as negative 1 plus the square root of 3i squared. And then we can go ahead and expand this. We know how to expand binomials. So it's the first one squared plus twice the product of the first one times the second one plus the second one squared. And what I mean there is we're doing a, well, let me do this in a different color. what I'm doing there is applying this, that a plus b squared is a squared plus 2ab plus b squared, right? A squared plus 2ab plus b squared. All right, so what does that give us now? Negative 1 squared is positive 1. 2 times negative 1 is negative 2 times the square root of 3i, plus this part becomes 3i squared. But 3i squared, we already know that's going to become just negative 3. So we have 1 minus 3 is negative 2. So negative 2 minus 2, radical 3i. All right. Now, let's see where else these complex numbers can come in. All right. So, what letter are we at? V. So W. Let's say that I said something like, solve the following. 8x squared plus 14x plus 19 is equal to 0. And not plus 19, I meant to do plus 9. There we go. Plus 9 is equal to 0. Now, you can try to factor this, right? You can say, let's factor this. And what would that give us? Let's say, so we have 8 times 9 gives us 72, right? We're trying to do the AC method. 8 times 9 is 72. And we think of two numbers that multiply to 72 but add up to 14. You're going to have a hard time. 1 times 72, 2 times 36, 3 times 24, 4 times 18. This kind of looks like it, but it doesn't work because in here they're both positive, so that means they need to be the same sign. So if these are both positive, you get 22. And if they're both negative, you get negative 22. So that doesn't work. All right. So then what else? What other options do we have? 6 and 12. That doesn't work. 8 and 9. That doesn't work. And then that's it. Those are all your options. So this is not factorable. So not helpful. Goes away. So what can we do? Well, we can say we can have the quadratic formula. And the quadratic formula was x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And, well, now all we need to do is plug stuff in, right? Because this is just based off the quadratic formula. So we have the negative of 14 plus or minus the square root of b, which is 14 squared, minus 4 times a, which is 8, times c, which is 9. All of this over 2 times a, which is 8. And well, what does that give us? Let's see, we have negative 14 plus or minus the square root of 14 squared is 196 minus 4 times 8 times 9. Let's do it this way. 9 times 8 is 72. 72 times 4, well, 4 times 2 is 8. 4 times 7 is 28. So we have 288. And all of this over 16. And then we say here, we have 196 minus 288. 196 minus 288 is negative 92. And then we would normally say no real solution at this point, right? But now we know about the complex numbers. So now we can say it's actually a complex solution. So in here, this is no real solution because the solution would not be a real number. But we can continue here and now say a complex solution exists. Now let's write that better. A complex solution exists. And by that we mean is that the number is going to have an imaginary component. So what we can do now is let's continue to simplify this. So we have negative 14 over 16 plus or minus the square root of 92. I'm going to write it as, the square root of negative 92. I'm going to write it as the square root of 92 times I, and all of this over 16. At that point, well, now we just need to simplify this, right? 14 and 16, they're both divisible by 2. So I end up with negative 7 over 8, right? and plus or minus 92. 92 happens to be 4 times 23. So we have the square root of 4 times the square root of 23. Right? 4 times 3 is 12, carry the 1. 4 times 2 is 8, and 1 is 9. And the square root of 4 is just 2. So this is just 2 now. And what we have here is 2 times radical 23 over 16i. And as our final answer, we can just reduce this and say that we have here just negative 7/8 plus or minus the square root of 23 over 4, not over 4, over 8. 2 and 16, they're both divisible by 2, so it becomes over 8i. Alright, so essentially, it's the same exact thing that you would do with the quadratic formula, but now you have the extra step of having to work with a complex number. And that concludes 2.4.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.